So let me introduce our next speaker, Siyuan Huang. Dr. Huang is a research scientist at the Beijing Institute of General Artificial Intelligence, which is BIGAI, directing the Center of Embodied AI and Robotics. He received his PhD from the Department of Statistics at the UCLA. His research aims to build a general robot capable of understanding and interacting with 3D environments like humans. His research has received multiple awards, including the Best Paper Award of Oral 2025 and several workshops as papers. Let's welcome Dr. Siyuan.
Okay, thank you for the introduction. And it's my great honor to be here to share some of our recent works in humanoid robot. And my name is Siyuan, and I'm currently a research scientist from Beijing Institute. Sorry. That's okay. From Beijing Institute for General Artificial Intelligence, aka BIGAI. And today, my topic is the 80% paradox for humanoid robot. So first thing first, let's revisit human brain. So basically from the left figure, we can see that there are three main parts from the human brain: the cerebrum, and cerebellum, and the brainstem. And here we can see that there are different lobes of the cerebellum, and there are different regions. Basically, they are dealing with different functions of humans, including the multimodal understanding, like the visual processing and the language, and also the understanding, reasoning, and plan. So there are basically 16 billions of neurons in cerebellum. And however, there are more than 80% of neurons here in brain are from cerebellum, about 69 billion of neurons. So this kind of neurons, they are taking care of control, balance, and coordination for human bodies. So here is the paradox of the human robot. So basically right now, people are using huge amount of compute and effort for 20% of the neuron of the brain. So basically we are expending like billions of dollars for developing models like VLA models and word action models. But actually we are using very little resources for the remaining 80% of neurons. So currently the controller for the human robot, they are relatively in small size, like millions parameters and MLP structures, and cannot be very generalizable. So many of my students or colleagues may ask me one question. So why we need to model the cerebellum with so many neurons? So let's check about some videos from the whole body coordinations. So here is a demo from figures that's showing that the human robot can actually using different body parts to do the coordination and balance and to achieve this kind of daily tasks. So for a whole body full-size human robot, so basically we can use the legs, the hands, and also the arms, the hips, the knees, and the ankles to do the coordination and finish this kind of interactions in our daily situations, like in the kitchen, bedroom, living room. And also for dexterous manipulations, the human hand can do very complex, like pen spinning, and also we can use the robotic hand to do the sliding and finger gating, this kind of in-hand reorientations for robotic hand. So this kind of interaction actually requires very high degree of freedom of interactions. But this kind of high degree of freedom actually causes the curse of dimensionality for humanoid controller. So assume we have n discrete states for a robot with d degree of freedom. So then the total state number is n to the power of d. And if n equals to 10, then for current G1 humanoid robot, we have 10 to the power of 29 states. And for the dexterous hand, for example, the Sharpa dexterous hand, we have 10 to the number of 22 states. So this kind of state, so some people may ask that for images and for language, we also have some high dimensional state, but each robot state is related to physics. They are not digital. They control the robot in real time. So it's harder for the controller to deal with this kind of high dimensional state space. So the controller is difficult to learn with like representation for dealing with such kind of representations, learning and optimization. And also the real world physics and dynamics, they are really complex. In terms of gravity, the context switching make it harder to learn and generalize for the humanoid controller. So most importantly, the so-called brain model, the BIGAI models and word action models, they are built on an oversimplified controller on some bimanual situations, and they cannot be easily extended to the current humanoid robots. So we needed more capable and more general control models for our humanoid robots. So here is an example from the figure. Actually, they have different systems for dealing with a general controller and general planner. So we have system 0 and system 1, and they have like hundreds of millions parameters. And then we have system 2 that can deal with the scene understanding and language comprehension. So this kind of structure actually tells us that we need a more capable and more general control models for humanoid robot to deal with the high degree of freedoms robot. And then we can have the planner on top of this kind of controller. So to solve such challenges, we propose an omni-stream recent work recently in RSS this year. So the work is trying to break the generality barrier in high dynamic humanoid control and is in collaboration with the Unity Robotics. So here is a brief demo of the work. So the goal of this work is trying to develop a general policy that can do the extreme dances using one single policies. For example, the backflips, the kung fu, and the K-pop, this kind of challenging movement, we can achieve all of these dances with one single policy. So here is a brief background about how to transforming this kind of motion capture knowledge to the motor intelligence. Basically, we have 4 stages. In the first stage, we have a reference motion, and then we can use a motion control policy to train the policy in the simulator and to learn by maximizing the tracking reward and get a pretty good policies in simulator. And then we can have a motor level PD controller for the real robot. Then we can transfer this kind of simulation policy into the real world. And we have seen remarkable progress in learning the specialist policies. And we have seen the performance by Unity Robot, the Ubot, and the Chinese New Year Gala. So basically, there are dozens of Siyuan robots, and they are performing with very, very difficult and very impressive this kind of Chinese dance, Chinese Kung Fu. But actually, this kind of movement or dances, they are all trained by specialist policies. So that basically means you need dozens of engineers and scientists to train dozens of policies for each movement. And you need to switch policies from one to another during the performance. And meanwhile, we are training the general policies, trying to fit like dozens of hours of motions and to learn the general policies, like GMT. But however, we have observed a phenomenon that along with the number of the skills increase, the fidelity drops significantly. The performance of the fidelity drops significantly. So that means more skill leads to lower motion difficulty and quality. So our goal of this work is to develop a scalable controller that's trying to maintain the extreme fidelity while scaling to diverse skills, like the blue figure shows. So in order to study the challenges, we actually ask ourselves about what is the limitation of scaling the real world humanoid robot control. So we have seen remarkable progress in character animation in graphics. So we have scalable pipeline for learning this kind of diverse and extreme humanoid skills. There are scalable learning frameworks, and there are no real world constraints. And for the real world robot, actually, we have a limited representation capacity for the model, and we have actuation constraint. We have complex dynamics that is difficult for a robot to learn in the real world. So there are basically 2 coupled bottlenecks. The first is the learning bottleneck. So it's still very hard to learn one single policy, control policy, that can scale to large scale, diverse, and high dynamic motions. And second is the physical bottleneck. So it's really hard for the real world robot to learn the high dynamic skills on the real world. For the learning bottleneck, there are 2 major problems. The first is the representations. So currently, people are still using policies like with structure like MLP with several million parameters to learn the the general policies. So there are limited capacities to learn to model such rich, diverse, and motion distributions. And second is the optimization difficulty. So when we are dealing with the multi-motion training in the RL simulation, we find that gradients from different motions interfere. So it's really challenging to learn like hundreds of hours motions using RL in real time. So hindering the stable learning of the optimizations. So with more expressive representations and more stable and well-structured learning objectives for this kind of scalable controller. And the second bottleneck is the physical sim-to-real bottleneck. So some people may wonder that the current sim-to-real can be pretty easy by using some domain randomization to deal with the sensor noise. However, it's still difficult for real-world situations. So there are a lot of actuation constraints. There are frictions, delay, multi-contact, and switching for real-world robots. So it's still very challenging. So our solution in OmniXchain is trying to decouple the learning and physical executions. So basically, we have two stages. The first is the scalable pre-training stage, trying to fit the hundreds of hours of motions into one single policy. And the second stage is actuation-aware post-training, trying to adopt the policies into the real-world physics. So the first stage, we try to use the generative models to train the general controller. So there are 4 steps. So in the first step, we can use some SOTA tracking policies to fit each single motions by using the BIGAI mimic to train the models. And then we can have hundreds of thousands of expert policies. And we can then distill this kind of policies into student policy by a flow matching method. So during each iteration, we can query the teacher policies, and then we can do the expert data labeling for each expert. And then we sample the teacher and distill them into the student. We clear the buffer at each iteration. We use flow matching optimization. So during each iteration, we can sample the teachers, and then we can do the online distillations. So the key design of pre-training is that it is generative with the flow matching, so it can be more scalable with the motion numbers. So right now we have like dozens of hours of motions, but in the future, we also can have like hundreds or thousands of motions. They can all be learned by this kind of learning paradigm. And on the right side, we did some experiment about how scalable the motion controller can be. So we ablate model with different size from 20 million parameters to 70 million parameters. And we saw that the success rate actually increases and also the tracking error decreases along with the increase of the parameter, the model size. And the second stage is the post-training. Actually, the real motors cannot produce arbitrary torques. So this is really different from the simulation situations. So from the left side, we can see that the torque limit actually changes along with the increase of the joint velocity. So there is an admissible region and also unattainable region for the real-world motors. So in simulator, we regulate the behavior of the motor so to make it more close to the real-world situations. So with this kind of techniques, the real-world behavior can be more, the policy actually get milder and more gentler. So the real-world behavior can be much closer to the sim performance. And also, we develop an energy-aware control methods. For the motor, we actually limit the power of the current, because if the power is too large, then the actuator will actually faces overcurrent protections for the unity actuators. We can see that when power is too large, it triggers overcurrent protection. So during simulations, we need to make the policy milder and gentler. So we're using this kind of penalties for the large power, and then the policy can be milder and be easily transferred to the real world. So, and we also increase the domain randomization during the post-training process. So basically, we have mild domain randomization for the pre-train, so the model can be more scalable and fit into more motions with a little bit domain randomization. And during the adaptation, we increase the domain randomization so that they can deal with the real-world physics and real-world dynamics. And we ablate the design of different post-training techniques, and we find that during flip and breakdance and acrobatics, this kind of techniques actually increase the performance and increase the success rate of some very high dynamic motions. So we did some experiment in ablation showing that OmniStream is actually very scalable to diverse and high dynamic motions in keeping both the fidelity and generalization capability. And also we did a bunch of real-world experiment and burning like dozens of unitary robots. So we have like 150 real-world trials for this kind of high dynamic skills. And it actually achieves like 90% of success rate on this very challenging movements. And here are some more examples of how we do the real-world experiments. It can achieve very challenging movement. I guess nobody in this room can do all of this, right? Like alternating pistol squats and consecutive Webster's flips, long breaking dance, and b-boying with the back handsprings. So in second part, we will discuss about how can we transfer this kind of human robot training into into controlling the dexterous hand. So in order to solve this, we propose tele-dexter towards human level dexterous teleoperation. So this is a work in preparation and will be released soon this week. So the goal of tele-dexter is to train a co-tracker for both the human hand and the object. So it can produce a teleoperation system that using an input of a human hand and also the object pose, we can do the tool use. Like the broom, we can use them to sweep the table and move the object. And we can use the hammer in both sides to install and remove the nails. So different from humanoid robot, actually controlling a dexterous hand is much more complicated because we don't only track the hand, we also need to track the objects. So for humanoid robot, the mainly contact only exists in the robot and the ground contact. But in the dexterous manipulations, there are much more contact between the robot hand and also the object. So the tracking goal includes both the hand target and also the object target. And compared with some previous like simple retargeting algorithm, like software-based retargeting, hardware-based retargeting, and simulation learned dynamic priors, like dexterity gen, right? The teledex actually owns several advantages, including the task-based alignment, executable command, and responsive. So basically, we can achieve very accurate teleoperation according to our policy. So here's a brief pipeline of method. So basically, the input is still the sequence, motion capture sequence, including both the hand gesture, hand pose, and also the object pose. And we designed several technical methods to learn policies, including the hybrid reward. We use a consecutive goal reach combined with a dance tracking reward to train the policy. And we use an action mask during the training in simulator so the policy can be easily transferred to the real world. And still we have curriculum that trying to learn the dance tracking first and do the goal tracking after first stage. So we sample the goal state from the in-trajectory motion capture sequence and cross-trajectory motion capture sequence. So we can do a consecutive manipulation and also the any-to-any translation of the object. And using this kind of teleoperation system, we can do the motion capture at the real time and then capture the state of the hand and also the object and use them as an input to control the robotic hand and also the object movement. 1 minute, okay. So here's a brief introduction about reference motion construction. So we can use a motion capture system to collect the fingertip position and also the object pose as the input for the system. So for this kind of system, we need a better retargeting module to do the data refinement. So the capture input is the object pose and also the hand pose. And we have a retargeting system to retarget them into the robotic hand and objects. And this is not enough, so we need to track the object with a policy. So dance tracking is not enough because they follow the trajectory path at each time step. So there is no room for contact adjustment. So our method uses sub-goal tracking. So basically we sample the sub-goal from the sequence of the motion trajectory, and then the policy can freely discover its own contact strategy between goals. So this enable regrasping, reorient, and finger gating. So in this sense, the reference motion defines what to reach, not how to move. And last is our hybrid reward design. So the dance tracking reward is trying to warm up the policy at the beginning, so help the learning to start. And then we have consecutive goal reaching reward that is trying to encourage the real sub-goal completion. And there is a curriculum from the low gravity to full gravity that's trying to make policy easy to do the contact establishment for the early stage in training. And also the tolerance is loose at the beginning and strict at the end, so we can gradually learn the precise and object tracking. Also, we tune the steps of the sampling from small one to larger one during training, so we can do local tracking with the dance reward first, and then we can do long horizon transitions. So here are some results. So we can basically do the teleoperation using the tool, like the hammers, the screwdrivers, and we can install and uninstall the light bulb using the teleoperation system with a very high success rate. And then we can control this kind of tool like the broom to sweep the table. And similarly, we can do the in-hand orientation using sharper hand with relatively less the central gap using the bunny, the cube, and cylinders. And also for other embodiment like the lip hand with 4 fingers, we can similarly do the same in-hand reorientations. And we can also do the any-to-any translation for this kind of object movement. Basically, the goal is sampled from an arbitrary state, and we can control the object to transit into this state. And last, we can train the autonomous policies according to dozens of demos from such operation system. So the policy can use a real sensor view camera and also a wrist camera to learn the policy, so they can install and install the bulb and achieve this kind of long horizon interactions. So basically, this is the talk of my today's presentation, and the main talk is about how to unleash the limits of the high degree of freedom humanoid robots with better general controller. And thank you all for listening. Thanks.